I want to make sure I talk about it now. So here's what happens. The t-distribution itself, in the real world, I need you to understand this. In the real world, it is rare to know the population standard, the population distribution. And because of that, what that really means is it is rare that we know the population standard deviation. Do you remember what we call the population standard deviation, by the way? Anybody know what we call the population standard deviation? No. I'll tell y'all. The population standard deviation is called sigma. It's rare that we know this. Really and truthfully, you hardly ever know this. Because in order to know the population standard deviation, you have to know every value in the population. And if you have small populations, then that's fine. But if you had small populations, you wouldn't need to do all these tests and stuff, right? So it's rare that we know this. And because of that, we have to use what we call our sample standard deviation, also known as S. So generally speaking, we're gonna have to use the sample standard deviation. And this value is equal to S. And it comes from the sample. We're gonna use S as an estimate for sigma. So most of the time, what you're doing is you're basing everything off of S, the sample standard deviation. And we always use this if sigma is unknown, the population standard deviation is unknown, which is a lot of the time, by the way. And because you have this unknown quantity for the standard deviation that you're trying to estimate, what ends up happening is we already want things to be normal, right? And in order for things to be normal, from the central limit theorem, what was the magic number again? Anybody tell me that? If I want it to be normal, what's my magic number again? What is it?
30?
I heard somebody. 30. It is 30, right? Anything that's 30 or bigger, look what happens to it from this picture right here. The distribution starts to approach a normal distribution like this. This blue one right here is a true normal. This is a true standard normal where it peaks, and look at the curve, look at the tails in particular. The tails are very close to the horizontal axis as you get close, as you go further and further off, which means there's very little area occurring in the horizontal axis part. When the distribution is around 30 though, it's pretty much normal as well. You get the same shape, but there's more area in your tails. You have more areas for the extreme values, is what this is saying. There's more area in these extreme values. When the distribution is less than 30, when that occurs, we don't really know if it's normal or not. We can assume that it's partially normal or that it's mound shape. It may be symmetric, but we don't know if we have this true peak with these tails. But what we do know is that because of all this estimating that we're doing, we need more room for error. And that error really occurs in the extreme values. Because what this is saying now, we can have more extreme values out here. We can have more extreme values. So you always have more area. This is called the T distribution. This is called students T. And in the T distribution, what ends up happening is you get the shape of a normal curve, right? And it becomes more normal as your sample size increases. So the bigger the sample size, you remember what we call the sample size, by the way? Sample size is equal to what? What letter? Do you remember? I'll tell y'all, it's N. The bigger the sample size, the more normal the shape. And here's what happens then. Because of that, we have all of these different T distributions. We have all of these different T distributions, all the way down from 1 all the way up to infinity, by the way. And the more numbers you know, the higher you go up, the more it starts to look like this blue curve. The less you know, the more it starts to look like this. I think that's a pink curve, maybe. That pink curve right there, right? So typically speaking, though, there are certain events where our sample size cannot be too big. For instance, certain experiments that we do, like if you wanted to test the test the rate at which test the force at which an airbag deploys in a car. Well, you literally have to run a car up against a wall, right? and watch the airbag deploy at a certain rate or at a certain thing, at a certain force, right? Now, what's going to happen there is we can only destroy so many cars before we start to run into a resource problem, a budget problem, right? So we can't do that 30 times. We may be able to do that 8 to 10 times. Because we're doing it less than the 30, our shape is not going to be normal like this. It won't be truly normal or close to normal like this. It'll be more mound shape. And that's okay because we have this distribution, the T distribution, which says, hey, even though we have this mound shape, we're going to account for extreme values falling out here and for out here by giving you more area out here, right? And what ends up happening is we use this distribution, and we have to use this distribution when my sigma, the population standard deviation, is unknown. Anytime sigma is unknown, you have to use the distribution. And what's going to determine the shape of the curve is what these things that we call degrees of freedom. These things that we call degrees of freedom. As you get more and more degrees of freedom, your curve becomes more and more normal. That's because your degrees of freedom, which we call DF, are equal to the sample size minus 1. So every T distribution is pretty much just like a normal distribution, by the way. They're all symmetric. They all have a mean centered, they all have a mean at the center, right? But here, it becomes more normal as your sample size increases. And every one of these curves is defined by this thing that we call the degrees of freedom, which are equal to n minus 1, the sample size minus 1. So the bigger the sample size, the more normal. The bigger the sample size, right? The bigger the sample size, the more degrees of freedom you have. Are y'all looking for these notes? Yeah, I need them. I'll put them in. Give me a second. Yeah, they should be in the chat now. So the T distribution is just like the Z distribution, by the way. And remember, for the Z distribution, we found that thing that we call the critical value. We found that thing that we call the critical value. And we find the critical value the same way that we did the Z critical value, right? We use Excel. We use Excel for, we're gonna use Excel here too, all right? And when you do this, here's what you need to have. This says that alpha is equal to 0.05 and n is equal to 64, right? So what that really means is what I'm gonna do on this curve is, for any curve I have, I'm going to, again, set the bounds of the curve. If the alpha is equal to 0.05, that means this is how much area is sitting on the outside. That's how much area is on the outside. That's your outside area, got that? So if 5% is on the outside, how much sits on the inside? Can anybody answer that?
95.
95%, thank you so much. That's 95%. And if it's 5% though, what do we say about this? How much sits on this side, on the left-hand side? How much is over here?
0.025.
Good, 2.5%. You're right, 2.5%. I should write it like that. I'm gonna write them as percents. And that means that 2.5 is also sitting over here, right? So that's how much area sits on the outside. So the first thing I'm gonna do is this. You need to realize that on the inside of this curve, by the way, on the inside of the curve that's the confidence level. Your alpha value sits over here. So this over here is half of alpha. This over here is also half of alpha, by the way. It's half of alpha sitting out there. To find this value, we're trying to find the T-stat. The T-stat sits right here. It's the right-hand critical value. They call it T-stat, I call it T-star. But either way, it's what you're trying to find. You're trying to find this value right here. And here's how you find this value. When we find this value, remember how we found it with the critical, what we found with the Z? We had to add up this part right here. We had to take this part right here and then add it to this part right here. So that's how we got that 97.5. Do you remember doing that? Yes. You remember doing that? Okay, cool. 97.5. And then the next part was this though. After that, to find this T-stat, what we had to do is this next. this is a little bit different. In the T-stat, you now have to give it degrees of freedom. You have to give what we call degrees of freedom. So if my n is equal to 64, what is my degree? What are my degrees of freedom equal to? Anybody can answer that? Degrees of freedom.
63.
63, good. Degrees of freedom are always equal to n minus 1. So your degrees of freedom are 63. So what you're trying to find is the T-stat with 63 degrees of freedom. We subscripted like that to let you know the degrees of freedom. And so I'm going to go in Excel and find this T-stat. And to do that, I'm going to use the T.INV formula. T.INV formula. So in Excel. So here I go, T.INV. So I'm going to do equals T.INV. The probability I have here, remember that probability is 95 plus 2.5. So it'll be 0.975. And then it wants degrees of freedom. The degrees of freedom here are 63. When I do that, I get a t-score of 1.998. So if we round that off, by the way, that's equal to about, let's go 3 decimals. Let's call it 1.998. Because I don't know what my math lab wants. But your TN, so you're going to do T.INV here, 0.975, 63 in Excel. This is the Excel command, by the way. And when I do that, I get this value right here equal to 1.998. That's how we find the T-stat. Look at the next one. I want to find alpha equals 10% and n equals 36. I'm going to draw a curve again. On the inside of my curve this time. How much on the outside, by the way, on this curve? On the outside is how much?
0.01.
So try it again. On the outside is 0.1, right? We're at 0.1. So how much is sitting on the inside? What percentage is on the inside?
99.
90%.
Or 90.
90%.
Oh, okay.
The next one will be 99. The next one will be 99. So this is 90%. Log in and log back out. Log back out and log back in. She can't hear me say that, huh? My fault. All right. So here's what happens now. Again, if there's 90% on the inside, that means how much is on the outside? Over here is 5%. And over here is 5%, right? But my T-stat only cares about up to this value right here. And so here's what we're going to calculate. We're going to calculate up to that value. What is that? We're going to calculate up to this value like this. And that's equal to 90% plus 5%. So that would be 95%, right? The other thing I need are my degrees of freedom. How many degrees of freedom do I have here? Degrees of freedom, how many do I have? 35. Thank you. I have 35 degrees of freedom. So I want to find the degrees of freedom for 35. T at 35, right? So in Excel, you're going to type in T.INV 0.95 35. That's the Excel command there. So when I do that, T.INV probability 0.95 degrees of freedom are 35. 1.68 or 1.690 is what we'll say. 1.690 is what we'll say. So this T-stat is 1.690. Class 1, I want to find the alpha equals 1%. So again, I'm going to draw a normal curve. right? Inside of this normal curve, here and here is my T. I want to find my T stat, right? On the inside of this normal curve is how much area?
99.
99%, right? So on the outside would be what on this side? How much on this side? Point, it's really written like this, 0.5%. It's really 0.05 when you add it to it, by the way. So it's 0.5 sitting out there, and I want to find all of that area up to this value again. All of that area up to this value. How many degrees of freedom do I have here at 100? How many degrees of freedom will I have? 99. Thank you so much. So I have 99 degrees. And on this one, I'm going to do in my calculator T.INV. I mean, on the Excel T.INV 0.99599. 0.99599. So I go in Excel. T.INV 0.995. And degrees of freedom were 99. When I do that, here's my T statistic, 2.626. So my T sat at 99 degrees is equal to 2.626. So we find the T critical value the same way we found the Z critical value. So we're adding this thing we call degrees of freedom. And this matters now because we can use the T critical value to do a test. We can reject and fail to reject based off of critical values. But in order to do all that, just like we did with any other test, we have to find what's called a test statistic. So the test statistic for the T critical value looks like this. And let me remind you what the test statistic looks for the Z critical value. When we did Z was equal to this, by the way. It was equal to X bar minus mu over sigma X over the square root of N. Look at how the formula changes for the T statistic. What do you notice is changing in the T statistic? What changes here?
The sample population.
The sample standard deviation.
I mean,
that's it.
Yes.
Good. That's it. This is the only thing that changes. This is now the sample standard deviation. And that's because we do not know the population standard deviation. This is now the sample standard deviation. This up here is the population standard deviation. We don't know that value, so we have to use its sample. And here's what's going to happen. We're going to go ahead now, and on our normal curve, we're going to find a t-score. That's what this literally is, the t-score. But it's on the t-distribution. And the t-distribution has a mean of 0. And what we're going to do is, when we find this t-score, this t-score is going to fall somewhere over here. Here's your t-score with its degrees of freedom, whatever that may be. And what I want to do now is I want to find the probability of finding a value that is as extreme or even more extreme than this value, if in fact your null is really true. That's called the p-value. So this part right here is called the p-value. Now, we're going to test with both the p-value and the critical value. And remember, here's what happens in the critical value method. In the critical value, what you're going to do, the critical value is what we just did, by the way. Critical value says, well, hey, you should be falling either here at T or negative T. Anything inside of here, anything inside of this region, we're going to, or it's plausible, which means that we would fail to reject HO. Anything inside of there we fail to reject. Anything falling out here though, or out here, any T value that's greater than those two values right there, we're going to reject HO. On this particular thing, here's what happens with the p-value. For the p-value, you're telling me now that your alpha, this is alpha, and over here is alpha as well. This is alpha, right? This is alpha. If I am less than alpha, then I fall into the reject HO region. If I am greater than alpha, which is anything over here, by the way, greater than alpha, anything over here, then I fall into the fail to reject region. So we've already done this, but I'm recovering that fail to reject HO region, all right? So we're gonna do examples. We're gonna do an example with this, all right? I'm gonna show you what I mean by all of this. So here we go. This says the mean number of sick days an employee takes per year is believed to be about 10. Members of a personnel department do not believe this figure is correct. They randomly survey 8 employees and ask them how many sick days they took in the past year. The mean for this sample is 8.4 with a sample standard deviation of 4.1. I need us to stop right there and understand what this is telling me. I've taken a sample and got a sample mean. The mean for the sample is 8.4. What do we call the sample mean, by the way? Somebody tell me that. What's the sample mean called?
Sigma.
Try it again. That's population. That's standard deviation. Keep going. What do we call the sample mean? X bar. Sample mean is called X bar. That's 8.4. The sample standard deviation is called S. That's 4.1. All right. Now, I've looked at 8 employees. That's going to be my sample size N. So N is equal to 8. Got that? I want to know at the 5% significance level, should the personnel team believe that the mean number is 10? So here's how we do this. We need to create a hypothesis. They're telling me, they're stating that the mean number of days missed is what? What's the mean number of days missed? Anybody?
10.
0.4.
10. So we're going to write that as 10. So this is mu is equal to 10. That's the first part. Mu is equal to 10. That's what they're stating it to be. They think that they do not believe this figure is correct. They say that it was more than 10 or less than 10. Well, they didn't tell us whether it was less than or more than. They just said it's not correct. So we're going to say this now, mu does not equal 10. We don't know the actual direction of where we're going. We know it's not equal to 10. They want me to test this at a significance level of 0.05, right? So in order to do that, here's what I need to do. Draw a normal curve. And on this normal curve, how much is on the outside?
0.05.
How much on the outside? 0.05. So that means how much on the inside? 95% on the inside.
95.
That means that there's 2.5% over here and 2.5% over there. Here's what I want to find. I want to find the T stat for this and the T stat for that one. I want to find the T and the negative T there, right? One's going to be positive, one will be negative. In order to do that, what do I need to press? What do I need to do? So this will be T dot INV. How much area am I calculating up to? All of this, right? Up to that value. So it's 95 plus 0.95. 95 plus 2.5. That'll be
0.975.
Good, 975. And I need the degrees of freedom. How many degrees of freedom do I have here? If N is equal to 8, what's my degrees of freedom equal to? 7. Thank you. So I have 7 here. So I want to calculate that, the T inverse 0.975 at 7 degrees of freedom. Let's go calculate that. When I get that, I do equals T dot INV. T dot INV. My probability is 0.975. Degrees of freedom are 7. Hey, by the way, what's wrong with the number 7 or the number 8 to begin? What's wrong with the number 8?
It's less than 30.
It's less than 30. So we don't really know the distribution of the population is normal. We're going to assume that it is normal though to make this work. Press that. Here's my critical value. 2.36, we'll say 2.365. 2.365. So I'm gonna come back over here. That means that this is equal to 2.365, and this right here is equal to a negative 2.365. So I have the regions, I have the region that represents rejection. Here's what's gonna happen. I'm going to reject if anything falls over here, or if anything falls over here. That is the region that represents rejection. So these are my rejection regions, right? If it falls in the red, it's failed to reject. We'll see what happens then. We need to calculate the T critical value. Well, the T critical value, T, is equal to X bar minus mu over S of X over the square root of N. Well, what is X bar for this particular distribution? What is X bar? Anybody tell me that?
8.4.
8.4.
Thank you. That's 8.4 minus the mean, the hypothesized mean. That's what they want you to give it. Mu is equal to 10. That's how much we hypothesized it to be. Divided by S of X, my standard deviation, which was 4.1, over the square root of N, which was 8. All right. So we need to calculate this right here. I have 8.4 minus 10 is this, negative 1.6 on top, divided by 4.1 divided by the square root divided by the square root of 8. Here's what I get. Negative 1.104, we'll say. We can go 3 decimal. Negative 1.104. So this is equal to negative 1.104. Well, the question is now, where does that fall at? If the mean is at 0 here, right? Negative 1.104 is falling somewhere right here. This is the negative 1.104 value. It falls somewhere right there. Where is it falling at? The rejection region or the fail to reject region?
Fail to reject.
Fail to reject. So what we're going to do here is we're going to fail to reject HO. So we're going to fail to reject HO. What does that mean? Why are we failing to reject HO? Think about the court case. If I fail to reject somebody's innocence, the whole goal that I'm trying to do, I'm trying to show that this person is not innocent. I want to reject their innocence. But in the end, I have failed to reject their innocence. That means that they are still innocent. Why are they still innocent? Well, they're still innocent because there is not enough evidence. There's not enough evidence to support HA, their guilt. In this particular case, they're telling me that the amount of days that on average that the person misses 10 days, right? Got that? The amount of days on average person missing any work year is 10 days. Now, the personnel department believes it's something different than that. They don't think it's 10. We go through this test with these particular statistics, and here's what we do. we failed to reject HO, which means that we're still saying that HO could be true. So the amount of days could be what? It could be 10, right? My goal again, though, is to show that it wasn't 10. I can't do that. Why can't I do that? Because there is not enough evidence to support HA. So this is the first way we can do this. And this is through the critical value method. It's called the critical value weighted test. Where we draw this curve and we put the t values on there like that. The other way is through the p-value method. And so if I want to do it through a p-value, here's how I do it through a p-value. We just found out already that we know that the alpha value is like this, where our rejection falls either here on this side or here on this side right here. This right here is equal to what? Can I remind what this equal to? What's that equal to again? It's sitting right here. What is it equal to? It's equal to 2.5. This right here is also equal to what? 2.5. So this is both 2.5% and this is also 2.5%, which is a total of what percentage, by the way? What's that percentage?
5.
Alpha is equal to 0.5%. Here's what I want to do then. If it falls in either this one or this one, I'm going to reject. So that means I have 5% area where I can reject that. And what that really means, if alpha falls anything less than this, or alpha falls anything more than this value, we're going to reject. Really, it's if anything less than this. So if anything less than this 5%, what that really means is unlikely to occur. If it's anything more than the 5%, that means it's pretty likely to occur. So what we've done is this then, we've gotten a t-value of negative 1.104, which is sitting right somewhere over here. Here's that negative 1.104. If I want to find the amount of area for this value right here, what do I do? Do you remember? How do I find that area? What would I do? We would use norm.dis, right? Norm.dis. Because we want to find the area of a normal curve. But we're not finding a normal curve, we're finding a t curve right now. And in your calculator, you have a new function. It's called t.dis. It's called t.dis. And it wants you to give it an area, a mean, or we're going to put a 0, a 1, and true back here. So in this particular case, we're going to do t.dis point, negative, not an area. It wants an x. It wants an x, or a t value. So we're going to put negative 1.104 first, 0, 1, and true. That's what I want to do. Negative 1.104, 0, 1, and true. Got that? So I'm going to Excel, calculate that. This is equal to t.dis, and want my x. My x is negative 1.104. The degrees of freedom, I'm sorry, that's what it wants, not a 0. It wants degrees of freedom. I need to go back and correct that. Degrees of freedom here are 7. And cumulative, you're going to set this to true. Press enter. This right here is your p-value. 0.153 is your p-value here. 0.153 is your p-value. So what that really means then is the amount of area that corresponds to this. Let me correct this real quick. This should be, don't put that. This should be degrees of freedom. This should be degrees of freedom. There you go. Or in this particular case, that should be 7. There. The p-value, the area that corresponds to this is 0.15. What was it? 0.15. Negative 0.150. We'll say that.
3.
Thank you. 0.153. Couldn't remember what it was.
Yes.
Thank you. 0.153, thank you. So we get 0.153, and here's what I want to know. Is that 0.153 bigger than this red area right here? Is that area bigger than or is it less than? We can see that it is clearly bigger than it, right? And here's what happened. Because it is bigger than that value, it falls in the safe region or in the fail to reject region. And so what I write is this: 0.153 is greater than 0.05. Because of that, we are going to also fail to reject. We're also going to fail to reject HO. Fail to reject the null HO. Why are we failing to reject the null? There is enough evidence. There's enough evidence here to support the alternative. There's enough evidence to support the alternative, all right? So this is how we do the hypothesis test again. We already talked about this, but now we're doing it with a T distribution. So the T distribution you can do it one of two ways. You can do it based on critical values, or you can do it based on a p-value. If the p-value is greater than alpha, you fail to reject. If the p-value is less than alpha, it's going to put you in your rejection region and you will reject, all right? So everything we've done up to this point has been a two-tailed test. We've always been looking at two tails. We're going to talk about these things that we call, well, we can do this one. Let's do this example real quick. A hospital was concerned about reducing its wait time. Never mind, I won't do this one yet. Let's wait on that one. The next thing we're going to talk about is what we call one-sided hypothesis test. So everything we've done so far has been two-sided. In a two-tailed test or a two-sided test, here's what that means. You've always looked at your normal curve like this. You've always been interested in both of the tails. In particular, you've been interested in your alpha being out here like that. And a one-sided test, here's how it's different. One-sided test, you're going to look at just this side, or it'll look at just this side. You're gonna put all your alpha in one side this time, all right? So all your alpha will go on one side. And so in a one-sided test, here we have, they're called directional tests. The null always has some kind of form of equality in it. And what I mean by that is whatever your null is, if you're doing a one-side lower tail test, it means you're checking the left-hand side over here. If you are checking the left-hand side over here, you're checking the left-hand side over there, you are doing what's called a lower tail test, a left tail test. That means your H1, I call it HA by the way, it's H1. Your H1 is less than. And if your H1 is less than, then your H0 has to be greater than or equal to. You always have to have the opposite sign with an equal sign. In a one-sided upper tail test, you're now testing over here. And if you're testing the upper tail, that means H1 is greater than. That means that the H0 has to be less than or equal to. You must always include an equal sign in your H0. Does everybody understand that? Some kind of equal sign has to be there. So we write these, here's how we look at it. Here's the lower tail example. Investigators wanted to determine whether children who were born very prematurely have poor cognitive ability than children born at full term. To investigate, they enrolled 100 children who had been born prematurely and measured their IQ in order to compare the sample mean to a normative IQ of 100. So the general IQ is going to be 100, right? We want to know these people who are born very prematurely have poor. So if it's poor, what does that mean? You should be less than what? Help me out. Yeah, help me out.
Less than 100?
Thank you so much. You should be less than 100. So here's how we write this. The null here is that H0 is that mu is greater than or equal to 100. Status quo. The alternative, H1, what I want to test is that mu is less than 100. This is called a left tail test. I'm going to check down here to see if that value falls out here somewhere. called a lower tail or left tail. An upper tail, a phone industry manager thinks that customers' monthly cell phone bills have increased and now average over the $52 per month. So the company wishes to test this claim. You want to test that claim, right? So status quo for this is that the average is going to be normally 52, right? So that means we're going to write that as less than or equal to 52. And then H1, what I want to test is that mu is greater than 52. I want to see if it's increased. Now, hey, hold on. Sorry about that. So here, what we're saying then, and the easiest way to write these directional tests is probably to actually write the alternative first. The alternative is always in the direction that you're trying to check. So when you're trying to check something, if you set the alternative first, the null has to be something with an equal sign in the opposite direction. All right. And that means you're going to test on this and never tell you're testing over here on the right-hand side. So we still use the critical value and t-value method here. The only thing that's different about this though, is that instead of putting the critical values in in two tails, we're only put it in one. So instead of splitting it like we've been doing with two tails, if you're doing a lower tail test, you're going to put all of your alpha on this side. This is now all of alpha. If you're testing an upper tail test, you're going to put all of your alpha on this side over here. Here's all your alpha again. The only thing different about this is we're not going to split. We're not going to split alpha in half anymore. We find the critical value. And we're going to find, we're doing T stats. We're doing T stats here, by the way. Well, it depends on the problem, I guess. It says in a one-tail hypothesis test where you reject HL only in the upper tail, what is the p-value for a z-stat of 2.0? Here's what this means. You're going to draw a normal curve. So I'm going to draw a normal curve here. They tell me it has to be in the upper tail. The upper tail. And I'm interested in the value of 2.0. And I want to find the p-value. The p-value is something as extreme or even more extreme. I want to find this area right here. How would I find that area? How would I find? Anybody want to tell me how to find that area?
Would it be like the 1 minus the t.inv?
We don't have to do all that. I just want to find the area. It's not t.inv. This is actually z. So because it's z, I actually want to just find the area for this. If I'm finding area, I do norm.dis. Norm.dis. And you would do 1 minus on this one though, if you're using Excel. 1 minus norm.dis because you're on the right-hand side. 1 minus norm.dis, 2, 0, 1, true. 2, 0, 1, true. That'll give you my answer for this one. Anytime you use z-stat, you have to do a norm.dis. And because you're on the right-hand side, you need to do 1 minus. Or if you want to, you can use the negative z-score. You can use negative 2.0. They're the same. So what I would do is I go to Excel. If I want to find that t-stat here, I'm going to do equals 1 minus norm.dis. 2, my mean is 0. My standard deviation is 1. Cumulative set it to true. I do 1 minus norm.dis. I'm doing 1 minus because I'm on the upper tail on the right-hand side. When I do that, I get this value right here, 0.02275, so 0.023. So the p-value that corresponds to this right here is 0.023. That's how much area sits out there, 0.023, which is not a lot of area, by the way. But you're putting all of your area in the right tail this time. Over here. In a one-tailed hypothesis test where you reject HA only in the lower tail, what is the p-value of a z-stat of negative 1.38? So let's draw it out again. I'm at here now, I'm at negative 1.38. I want to know how much area sits as extreme or even more extreme. That's what a p-value is. As extreme or even more extreme than this value right here. So because I'm in the left tail this time, I only need to do norm.dis. And norm.dis, I'm going to do negative 1.38, 0, 1, true. Negative 1.38, 0, 1, true. And that'll give me the p-value here. So to do that, I get again negative 1.38, 0, 1, true. Here's my p-value at 0.084. 0.084. So that means that in this tail right here, the area is 0.084. So p-values for one tail, for left, for upper and lower tails, how you find them? You use norm.dis. If you want to find a critical value, which is the next examples, in a one-tail hypothesis test where you reject HA only in the upper tail, what's the critical value of the test of the T test statistics with 10 degrees of freedom at the 0.1 level of significance? What does that all mean? Draw a normal curve. All right. And in this normal curve, I want an upper tail. So that means I'm on the right-hand side. And I want 1% level of significance. I want my alpha to equal 0.01. Normally, we would split this up in half. But because we are in one tail, all of that 0.01 is going to sit right here. All of that 0.01 sits right there. So my question is, then, because I'm in the upper tail, I want to find the t-stat. And this has 10 degrees of freedom. So I want to find the t-stat at 10 degrees for this value right here. If I want to find how much area is up to this point right here, up to this point, right? How much area sits below this point?
0.99.
Thank you so much. So we're going to do this back here. That's 0.99, that's 0.01 there, right? When I do this, and I want to do, because I'm talking about a t-stat, I'm going to do t.inv. The area below this value is 0.99. That's what I'm going to put back there. And I need 10 degrees of freedom. That is going to be my T critical value. All right. That is going to give me the T critical value there. So when I do this in Excel, because I put it all in one tail, the only thing that's really different, by the way, is that you are not cutting that alpha in half. So I'm going to do T.inv 0.0.99. Degrees of freedom are 0.0 or 1.0. 10, I'm sorry. Here's my T critical value, 2.764. 2.764 is my critical value here. And this time, here's what I want you to understand. You're only going to have a positive critical value here. This will be 2.764. There is no negative because you're checking only in the right tail. And the right tail has to be a positive number. So in the last it says, in a one-tail hypothesis test where you reject HA only in the lower tail, what is the critical value for a t-test statistic with 20 degrees of freedom at the 0.01 level of significance? Let's change this. Let's do it at the 0.05 level so you understand it too. So you understand the different levels of significance. Let's change it to 0.05. So here your alpha is equal to 0.05. And this time we are in the left tail. We're in the left tail right here. How much area is below that, by the way? How much area is below there?
0.05.
0.05 is out here. 0.05 is sitting out here, right? So here's your 0.05. So when I do this one now, here's what I need to do. I only care about the area up to this T-stat at, how many degrees of freedom do I have? 20 degrees, right? So I'm going to do T.inv. My area up to there is 0.05. My degrees of freedom are 20. So I'm always calculating, by the way, I'm always calculating to the left of the T value. I calculated left here. I also calculated left here, by the way, to get this T score, to get this T critical value. You always calculate to the left of to get the T critical value. When I do that, I get equals T dot INV 0.05 degrees of freedom are 20. Negative 1.725. So that's how you get the critical values, the T critical values that you're testing with them. And again, what's going to happen is when we just start doing our T statistics, when we calculate the T statistic, right? If it falls inside of this region, we reject HO. If it falls inside of this region now, we're going to fail to reject HO. That's what that T critical value does for us. So let's look at an example. It says the Washington Metropolitan Area Transit Authority said a bus fleet reliability goal of 8,000 bus miles. Bus reliability is measured specifically as the number of bus miles traveled before a mechanical breakdown that requires the bus to be removed from service or deviate from the schedule. Suppose a sample of 64 buses resulted in a resulted in a sample mean of 8,210 bus miles and a standard deviation of 625 bus miles. At the 5% significance level, is there evidence that the population mean bus miles is greater than 8,000 bus miles? So what we need to do, come up with an alternative. Come up with the alternative here. We want to test to show that it is greater than 8,000, right? So I know that H1 has to be mu greater than 8,000 miles. And if H1 is that, then the null is that mu has to be the opposite and equal to 8,000 here. That's your null only alternative. Now, I've gotten a value of 8,210 miles for my sample mean. My sample mean here is 8,210 miles. So X bar is 8,210. My standard deviation came from the sample. It's a sample standard deviation. So that's S is equal to 625. That matters because it tells you if I use a T critical value or a Z critical value. Because it's a sample standard deviation, I'm going to use the T critical value. Because I'm using S, I always use T. My N here was equal to 64 buses. If I want to find the T statistic, T is equal to X bar, 8,210 minus the hypothesized mean mu, which in this case is 8,000, divided by the standard deviation, S of X, over the square root of N. So in case you forgot that, I'll write it up here. T is equal to X bar minus mu over S of X over the square root of N. That's the T statistic. So when I calculate that, I get 8210 minus 800, divide that by 625 divided by the square root of 64. I get a T statistic of 2.688. That is my T statistic, 2.688. Here's what happens next. I'm going to draw a normal curve. And because this is this symbol right here tells me what kind of test I'm doing. I'm doing an upper tail test. Draw a normal curve. I'm doing upper tail. So I need to find a T-stat. A T-stat up here at 64, that means I have 63 degrees of freedom. Right, the T-stat is 63. And here they tell me that my alpha level is set at 5%. It's set at 5%. So how much area is going to sit out here in this tail? Can anybody tell me that? How much area sits in the tail?
5%.
5%, thank you so much. So this is your alpha equal 0.05. I need to find the T critical value at 63 degrees that corresponds to this. If this is 5%, remember I want to measure up to this and below it to get this T value. So there's 5% this way. How much sits back this way? How much is back this way?
95.
95, good. So I need to do this when I do this particular thing in my calculator. T dot I and V, 0.95, 63. T dot I and V, 0.95, 63. So here, T dot I and V, 0.95, 63. There's my T critical value, 1.669. So that means that this value right here is 1.669. I found a T critical value of 2.668, which is somewhere out here, right? That's my critical value, 2.688. Is it falling in this is the fail to reject? This is the reject HO region. Which region do I fall in here? Fail to reject or reject?
Reject.
I'm going to reject HO. Why am I rejecting HO? Why am I rejecting that the bus mileage reliability is less than or equal to 8,000? Well, there is enough evidence to support HA here, or H1, I'm sorry, H1 here, which is that the bus reliability is greater than 8,000. Based on what we've gathered, there's enough evidence to support that. Hey, that's the T critical value method. You could also do it through the p-value method. You can find a p-value. To find the p-value, we're in the upper tail right here. We got a z-score of 2.688. I want to find the probability that T is bigger than or equal to 2.688. So I was using p-values. So I'm using the p-value method. Again, I'm going to take that curve here. Here is the value that I got. That's 2.688. I want to find that area right there. This is the p-value. To find that p-value, I would do T dot dis. And actually, I would do this. Because I'm on the right of that p-value, I need to do 1 minus T dot dis. 2.688, right? Degrees of freedom are 63. Cumulative, you're going to set to true. So when I do that like this, I get equal to T dot dis 2.688. Degrees of freedom are 63. N is equal to cumulative, we're going to set to True. I don't know what I'm doing there. There. True. There. That's the value I get. Remember, I have to do 1 minus that. I forgot to do 1 minus. 1 minus this answer. There's your p-value. 0.004. So 0.005 is what we'll say. And a quicker way to do this, by the way, is to just do, if you're doing the right side, is to do the negative version of it. It'll always be easier to do negative, no matter what you get. So if I do t dot disk, .668 degrees of freedom, 63 cumulative TRUE true. I'm sorry, I need to make this a negative. Come up here and do it. Negative 2.688. But do it like that. See how it gives me the same value, but it gave it to me quicker. So if you do it from the right side, always, if you do it, whatever you do, when you do any one of these problems like this, just do the negative z-score in Excel. It'll give you the right p-value. That's what I'm trying to tell you. So my p-value here is 0.005. This is equal to 0.005. And again, what we're going to do is we compare the p-value to the alpha value. So my alpha is at 0.05. Here's what I have. 0.005 is less than 0.05. And because of that, this tells me also to reject HO. So both tests tell me to reject HO. One uses the critical value, one uses the p-value. Most software, when you do this, uses your p-value, which is nice because it makes it easier like that. All right, and the last one says, a hospital was concerned about reducing its wait time. You're reducing the wait time. A targeted wait time goal of 25 minutes was set after implementing an improvement framework and process. A sample of 326 patients showed the mean wait time was 23.18 minutes, the standard deviation of 16.59 minutes. If you test the null hypothesis at the 10% level of significance, is there evidence that the population mean wait time is less than 25 minutes? So again, we start this. It's easier to start with H1 on these type of problems. You want to know if it's less than 25 minutes. So what are we going to say? Mu is less than 25 for H1, which means that for HO, mu has to be greater than or equal to 25. Flip the signs around. Y'all okay with that?
Yes.
All right, thanks you guys. I appreciate your talking. Thank you so much. So here, the sample mean is X bar equals 23.18. The sample standard deviation, again, this came from the sample, that is S of X is equal to 16.59. Because it's a sample standard deviation, it's going to be a T distribution. You're using the T distribution, your T stat. My N is 326. So when I calculate this, the T stat is equal to X bar minus the mean. The hypothesized mean here is 25. Divided by S of X over the square root of my N, which is 326. So if I calculate that, 23.18 minus 25 divided by 16.59 divided by the square root of 326. Here's what I get. Negative 1.981. Because this is a one-sided test, right? I have all of my alpha, which in this case, my alpha is equal to, they said at the 0.1 level, so alpha is equal to 0.10, all in this tail over here. So I need to find here's what I need to find, the T stat. How many degrees of freedom do I have here? 325. The T stat at 325 degrees of freedom. That corresponds to this critical value. So on this one, I'm going to do T dot INV. How much area do I have sitting up to this point right here?
0.10.
And so I'm going to 0.10 and then 325. So here equals T dot INV 0.1025, 325. Negative 1.285. Negative 1.285 is that value. So this T value is equal to negative 1.285. So my value of negative 1.981, where does it fall at? Is it in the rejection region or the safe region? Reject or fail to reject? What do we fall at?
Reject.
Reject. Good. You're falling out here somewhere. Here's your value of negative 1.981. We're going to reject H0. We're rejecting H0 because there is enough evidence to support H1. And again, what this is really saying is you're going to reject that the wait time is greater than or equal to 25. There's enough evidence to say that you have reduced this wait time to 125. If I want to use the p-value method, right? If I want to use p-values, all I got to do, this is actually easier because it's a left-hand p-value already. You're going to do t dot dis. You're doing up to negative 1, you're doing up to negative 1.981. So the p-value method works like this. Negative 1.981, right? Degrees of freedom are 325. You're gonna go true. So I did that. Equals T dot dis. Degrees of the value was negative 1.981. Degrees of freedom are 325. Cumulative was set to true. There. Here's the value for the p-value, 0.0242. So 0.024. So your p-value is 0.024. We compared the p-value to the alpha value. So 0.024 is less than 0.1. If the p-value is less than the alpha value, we're going to reject HO again. So you can reject based off the p-value or the critical value. You just do whatever you feel better doing, or whatever that whatever my math lab will tell you to do, you can do it like that too. But you can reject off either one, all right?